A new state of matter discovered at Earth's center. Scientists have uncovered compelling evidence that Earth's inner core, long assumed to be a rigid ball of solid iron, actually exists in an exotic superionic state, a phase of matter that is neither fully solid nor fully liquid. In this strange regime, carbon atoms drift rapidly through a crystalline scaffold of solid iron, giving the inner core an unexpectedly soft, almost fluid-like character. If you like my content and want to listen more interesting science stories like this, then subscribe my channel, and don't forget to like and share this video with your friends and colleagues. This discovery resolves decades of geophysical puzzles, including the anomalously slow seismic waves observed in the core and its unusually high Poisson's ratio. It also points to a previously unrecognized source of energy that may help power Earth's magnetic field. A paradox at the center of the Earth. The inner core lies beneath the turbulent, molten outer core and is compressed under conditions so extreme, more than 3.3 million atmospheres of pressure and temperatures rivaling the sun's surface, that its iron-rich material should behave like an ultra-dense solid. Yet, seismic observations have consistently shown that 1. Shear waves travel through the inner core far more slowly than expected for solid iron. 2. The material exhibits mechanical properties closer to soft metals or even butter than steel. This contradiction raised a fundamental question. How can the inner core be solid and yet behave as if it were partially molten? Superionic matter, a long-suspected but unproven possibility. A major study published in National Science Review now provides the strongest answer yet. Led by Professor Yu-Jun Yang and Dr. Yu-Qian Huang of Sichuan University, with Professor Yu He of the Chinese Academy of Sciences, the research shows that under inner core-like conditions, iron-carbon alloys transform into a superionic phase. In this state, iron lattice remains solid and ordered, forming a stable scaffold. Carbon atoms move freely, diffusing through the lattice as easily as molecules in a liquid. This atomic mobility dramatically reduces the rigidity of the material, matching seismic observations. Professor Yang explains, under inner core conditions, iron atoms become highly mobile, moving through the iron lattice like children weaving through a square dance, while the iron framework stays solid. This superionic phase produces a remarkably low shear velocity. Experimental proof under extreme conditions. While computer simulations in 2022 hinted that the inner core might behave this way, experimental confirmation had remained out of reach. The new research overcame this barrier using an advanced dynamic shock compression platform. The team blasted iron-carbon samples to 7 kilometers per second, momentarily recreating the extreme pressure up to 140 GPa and temperature around 2600 Kelvin of the inner core. By combining in situ sound velocity measurements and high-fidelity molecular dynamics simulations, the researchers observed a sharp drop in shear wave velocity, a large increase in Poisson's ratio, and direct evidence of rapid carbon diffusion within a stable iron lattice. These signatures match those inferred from seismic studies of the real inner core, a dynamic core that influences Earth's magnetism. The emergence of a superionic phase inside the inner core carries profound geophysical implications. 1. Seismic anisotropy. Direction-dependent variations in wave speeds, one of the inner core's long-standing mysteries, may arise naturally from the directional flow of light elements within the ordered iron lattice. 2. Energy for the geodynamo. The motion of mobile carbon atoms may inject additional energy into the outer core's convective system, supporting the geodynamo that sustains Earth's magnetic field. As Dr. Huang notes, atomic diffusion in the inner core represents a previously overlooked energy source for the geodynamo. 3. Revised models of light element behavior. The findings show that interstitial light elements, especially carbon, play a far more influential role in shaping the core's physical properties than earlier models assumed. A shift in how we view Earth's deep interior. According to Professor Yang, these results mark a major conceptual shift. We are moving away from a static, rigid picture of the inner core and towards a dynamic one shaped by the flow of light elements. This discovery could reshape how scientists model not only Earth, but also other rocky planets and large exoplanets. Identifying a superionic phase at our planet's center offers new insights into how planetary magnetic fields evolve, how cores crystallize, and how deep interiors transport heat and energy. The research was supported by the National Natural Science Foundation of China, the Sichuan Science and Technology Program, and the CAS Youth Interdisciplinary